The topic to be discussed here is feature extraction for synthesis of complex material microstructures. It's been widely accepted that the different microstructure of the same material corresponding to different property. Let's look at Type 64 as our showcase. Different patterns of microstructures of Type 64 has totally different material properties of interest, such as fracture value. So, how could we design a microstructure that has desirable material properties of interest? Before we go into the step of design, let's first of all consider an efficient way to characterize the microstructures. Correlation function-based method is trying to estimate the property of two random points that drop into the same phase. The assumptions for the microstructure are isotropic and homogeneous. In this case, the microstructure are characterized by parameterized correlation function. Descriptor-based method is trying to manually define some variables by describing geometric characteristics of the particles, such as cluster distance, grain orientations, grain sizes, and so on. Supervised learning method is to train a supervised model, such as a classification tree, by considering the neighborhood of the target pixel as inputs. In this case, a conditional property between the neighborhood x and the target value y could be derived. The assumption for this method is that the microstructure follows Markovian random field. The spectral density function-based method is to figure out the power spectral density function of the material microstructures by assuming it's a quasi-random nanomaterial system. The limitation for current method is that it has some difficulties to preserve features of complicated material microstructures, such as Type 64. We try to characterize it by a causal model from a supervised learning method. The performance is not satisfied with different window sizes. So we brought the idea of the deep leaf network from computer science community to help us to address this issue. Deep leaf network has been widely used in feature extraction for classification purpose, but we want to see if we could directly use the high-level features that we have extracted to generate new images. In this case, a 5-layer deep leaf network has been built, which could help us to reduce the dimension from 40,000 to 30, and also by randomly generated from the 30 dimension, the reconstructions are visibly and statistically similar to the original samples. However, by the nature of the deep leaf network, the reconstruction size could not be larger than the input samples. However, by the nature of deep leaf network, the reconstruction size could not be larger than the input samples. In this case, a hybrid model has been built by using Markov random field to model the distribution of the activation of local material microstructure patterns. As we could see, the reconstruction size is no longer an issue, and the statistical similarity is still preserved. Finally, we want to show our appreciation to Dr. Honglak Li's group from University of Michigan and Dr. Wei Chen's group from Northwestern University. Thank you.